So let's see others. Okay, so oscillating polynomials is a in this point it is like the collocation polynomial, which also have the things that it also have some collocation at the derivative of some. It has some collocation on the derivative up to some order of derivatives. Okay, it means pxk, which is equal to y of xk. So xk are the points where it is coinciding. Similar way, p dash of xk, any derivative of also it can be equal. Okay, for some order, maybe in here we are dealing with the first derivative. So in some point also we can have uh, second derivative also. Okay, so we are not going that far now. Okay, in some cases it go higher order as well. So we are keeping our polynomial in this description. Okay, in the simplest oscillation, it is equal to the sum point, original point, as well as the derivative points. Okay. Okay. It's not. It doesn't have much thing to study here anyway. We just see one example and we finish it. Okay. So one of the example it says for this oscillating polynomial is Hermite's formula. So I think it's new to you, or you may heard this word somewhere. Okay. Or otherwise you just go and search around what is Hermite formula and so. Okay. Hermite's formula exhibits a polynomial of degree 2n plus 1. So it goes up to the point of 2n plus 1. It means what? So if I say P2, so this is a polynomial of degree up to what? Up to 2, no? So for example, A0 plus A1 x square. That's all. Okay. If it is Pn, you have to go up to An xn. Okay. But in similar way, if this Hermite polynomial is a degree of 2n plus 1 or less, okay, which has the first order oscillation, this one. So this is one of the this Hermite's formula's equation. It means Px equal to summation I is equal to n uix plus yi. It means what? U1x of y1 plus u2x of y2. Okay, up to, plus we have to go up to n. Okay, un of x yn. Okay, so these are the points, proper point with some coefficients. Okay, and then we have to start with the v1, let's say v1x of y1 dash. So we are taking our derivatives in some point. So this is our Hermite formula polynomial. Okay, Hermite formula. So it goes up to again vnx of yn dash. Okay, so in here yi and y dash I are the values of the given function and its derivative. Okay, given function and derivative at xi, at the point xi. Okay, similarly this uix and vix are polynomial. Okay, having properties similar to the Lagrangian multiplier. Okay, where we have heard this word, I think HM people may remember. We yesterday only we told these things. Okay, so Lagrange multipliers. Okay, I'll show you for in here we are defining the Lagrange multipliers in a give me a second. Okay, in this way. Okay. Okay. So Lagrange multipliers in this form, which has the numerator as well as denominator. So this is a polynomial, no? Lagrange Lagrange multiplier, which also if you are multiplying this will come. So what is happening is, so if it is LIX means you first in the numerator you have to subtract the each element by x, okay, x1 up to x minus xn. In the denominator you have in the point xi, now we are, if it is xi at the point xi, okay, you have to multiply, sorry, subtract by xi to x0, okay, xi to x1 up to xi to xn, okay. So this is we called as a Lagrange multiplier. So yeah, so you don't need that much anyway, but for some reason you have to know, okay. Please write down this Lagrange multipliers. Okay. So we use the notation LIX, okay, Li of x. So they are defining for this example, okay, no need much calibration away. So here they say this UIX and VX are polynomial having properties similar to the. Okay, I think power cut. Power cut, I think connection. Okay, so. Okay, so here we are in. So this UIX and VIX are we called as a Lagrange multipliers, where UIX has been defined in this way, VIX in this way. We don't need those things, okay. Anyway, just to know where these oscillating polynomial has been used, okay. So it has why we are seeing these things, because please write down whatever these things, okay. So this UIX, VIX are the polynomial Lagranges. So Lagranges we have seen already. So yeah, so why we studying is this Hermite's formula can be exhibits using this oscillation polynomial, where it is equal to summation of I is equal to 0 to n of UIX yi. So in some points of original values, which as well as the derivative, okay. So in here, in this UIX and VIX are in this form, okay, Lagrange multipliers form. Okay, that is one of the example for oscillating functions. So yeah, that's all about the oscillation polynomial. So if you're interested, you can check that our reference book, Numerical Analysis Charm series, for some question related to this one. I think one of the chapter has the name oscillating polynomial. So you can see some examples has done. It's they also have some solutions, so you can go through if you're interested. Okay. So yeah. So let me continue our last polynomial. Okay. That is one of the main very important one, hopefully. Okay. For your further studies. We may use these things in number of ways in our courseworks. And this is called as a Taylor polynomial. So Taylor is a famous mathematician, as well as he has gave so many results. In that way, this one is a Taylor polynomial. with his name as well. Taylor polynomial is the ultimate on oscillation. Here also the oscillation coming. Okay. So in the sense of the Taylor polynomial, so you must know how to give the formula for each polynomials. Okay. So we have seen 1, 2, 3, 4 polynomials. You should know how to write the formulas for each polynomials. Okay. So here the Taylor polynomial is in the form of Tx equal to summation I is equal to 0 to n. Okay. Tx equal to, it's a summation. So you have to add each term. Okay. It's in the form of y of I, okay, x naught divided by I factorial. Okay. Here x minus x naught of I. So we at the point of x naught, okay, we are having the polynomial. Okay. So if you wanted to have the approximation at the point of x naught, this will be the formula. The formula will be, yeah, give me a second. Okay, in here, this is the derivative notation. Okay, it means what? Y dash, y double dash, like that. Okay, this will be y1, we call. This will be y2. So up to you can have yn, which is equal to yn is equal to yn, no? So like that. So this is we called, okay, write down as a note. After writing the formula, write a note. It says, so ultimate in oscillations at the argument x naught. Okay, so you can write here at the, okay, sorry. So continue this one. The Taylor polynomial is the ultimate in oscillation for a single not the note. Okay, not, I'll do that later. You just continue this sentence. The Taylor polynomial is the ultimate in oscillation for a single argument x naught. Okay, so Taylor polynomial we are finding for at the argument of x naught. Okay, one of the point. Okay, given point. So for the note, write down the values of polynomial and its nth derivatives required to are required to okay, I write the continuation here. Okay, are required to match the given function yx. So what we are doing is the values of polynomial and its nth derivatives are required to match the given function. So to write the Taylor polynomial, we need the nth derivative of that functions. Okay, so in that sense, that is pi of x naught, which is equal to yi, it's a x naught. So in here it is denoted in the derivative. Okay, it's like a where I is equal to 4, I is equal to 0, 1, 2 up to n. Okay, n derivative we are taking. So can anyone tell me what will be the famous polynomial we can say as the example of Taylor polynomial? Taylor polynomial example. So that you already seen somewhere. Even in element differential equation also we have seen one of the kind of polynomial which is derived from the Taylor polynomial. Anyone? Like the polynomial which is in the form of this way, something a naught plus let's say 1 factorial of a1 times x, a2 over 2 factorial x squared, something like that. It means like this. Okay, I think here 1 2. It's like, do you remember? We have seen in our Picard iterations kind of example, like ex. Okay, those kind of value only here. Okay, it's like okay, I'll erase this window first of all. So it is like this. If you put I is equal to 0, this will be 0 factorial of 0 factorial will be 1. So this will be y0 x0 x minus x naught. So it is like this. Something constant plus x minus x naught of y1 x naught of 1 factorial, like that, x minus x naught whole thing squared, while double dash x naught of 2 factorial, like that goes. Okay, so something in this way it is. So this is we called as a Taylor polynomial. Okay, we can see further also. Okay, so also you just check around what it is means of Maclaurin. I think I have told you to see already. So this is kind of, we are deriving from here. Okay, Maclaurin formula. You just go through this one also as a homework. Okay, see how these two are derived. Okay, let's do one example so we can finish that thing. Maclaurin. Okay, R-I. Sorry, give me a second. Maclaurin formula. Okay, so just to remember the Taylor polynomial. Okay, that's enough. Anyway, let me continue some examples on it and we can finish the polynomial today. Okay, so this is one of the questions. Okay, what it says is find the polynomial px, okay, of degree n or less, which together with its first n derivative take the value y0, y01, y02, y0n for the argument x0. Okay, so just write down the question, don't write the answers. I will do that. Okay, so otherwise you won't understand. So just write down this question. Find the polynomial of degree n for argument x0, which together n derivative take the values this one. Okay. So they are asking you to find a polynomial px of degree n or less, which together with the first n derivative takes, so y naught, so according to the variable of y naught, okay, and the derivative of y naught, derivative of y2, yn for this argument x naught, okay, using the Taylor polynomial, we're going to find it out. Okay, so let me go back to the whiteboard. Okay. So now So let's do the solution. Okay. Polynomial of degree n, polynomial of degree n can be written. Okay. So for the argument x naught. Okay. So actually, we have seen our px is equal to a naught plus a1 x plus a2 x squared, like that. Okay. So this is like a x into like x minus 1, x minus 2. We take that uh, like this will be the factors of this polynomial, then we can find the solution, that kind of. Okay. But here, if they give you the argument, the point where it is have to find the polynomial, okay, you have to write the polynomial p of x equal to a naught, yes, a1x. So here we put only x, no. So if it is the argument coming, you have to turn around this uh, polynomial in this way, x minus x naught. Okay. Again, what will be the next term? Can you send me the answer? And the last term. So we are finding for n degree. So it should n an. So what is this one? This is a2 anyway. What is this one? Can you send me the answers? According to our knowledge of polynomial, we have written. So you can take, you can take this one as we are finding at x naught is equal to 0, no? It's kind of x naught is equal to 0. So this will be 0, this will be 0, like that. So if it is something at argument, some value of x naught, how it will be changed? Can you write this and this down? So it is continuing, okay? Can I send your answers? The answers. Okay, yeah. X minus xn minus 1 now. 27, can you check your answers? No, 144. Check your answers. No. 04. Wrong. 140, correct. 157, wrong. So what I said to you is, we are fixing the argument now. X naught. Wherever it is, here x naught is equal to 0. Wherever it is, we don't have no anything. If I say 0, did you put 1, 2, 3 like that? No. You take everywhere x naught is equal to 0. Like what? You have to take everywhere as x naught. No. 112, can you check your answers? Yes, 0 2, okay. So this will be A2 correct. So whatever this one squared, okay, x minus x naught squared, not x minus x1, okay. Similarly, if you go here, x minus x naught to the power of n. So we are finding at the argument of x naught, no. So we fixing the x naught and we are taking off the from x and taking the powers, okay. Yeah, fine. So let's continue our solution, okay. So this is a polynomial of degree n can be written the argument x naught, okay. Px equal to a naught plus a1 x minus x, this one, okay. So now to get our, what is that? What we have to find is, we have to find one polynomial which has the degree n. Yes, this we have written. We have to have the value of y naught, y naught 1, y naught 2, this kind of answer you have to have. Okay, but we have a naught, a1, a2, like that, no? So we have to find the answer for that. Okay. So first of all, let's say this is equal to what? Y of x, no? Yeah, give me a second. Yeah. So we know p x naught is equal to, we are taking as y naught. Okay. So p at the argument of x naught, we call that y naught. Okay. So let's see how to get y naught 1, 2, 3. Okay. That's what we're going to find. So let this one. Okay. Then take this as the equation number 1. Okay. Now successively differentiate equation 1 gives, okay, gives. Successively differentiate equation 1 gives, okay, we're gonna differentiate with respect to what? With respect to, can you answer me? Yeah. Is that x naught or x? X naught is like a constant, no? It's just a 1 point, okay? So x is a variable. So this is depend on x, no? So differentiate with respect to x. We don't need to tell that, okay? Differentiate with equation 1 gives. Let me, yeah. Shall I erase this window? Can you take down whatever you need? Meeting also going to finish within 10 minutes. Okay. Can you, yeah, write down whatever you need, okay? I'm gonna erase this one. Okay, now, yeah. If you differentiate, let's say my P1 of x, which is equal to, what you'll get? So my Px, I got a naught plus a1 x minus x naught plus a2, something like that. Okay, so what will be P1 of x? So this will be a constant, no? So this will be 0. Okay, here a1x, what do you get? If you have a1x, what do you get? It's a a1, no? Am I right? So a1x differentiate with respect to x will be x. X and x will be 1. So the a1. Okay, we are considering x naught as a constant. Okay, constant point. Similarly, if you get, what is the next term? So it goes up to, so n into an x minus x naught to the power of n minus 1. So we know that differential equation of polynomial, no? So for example, if my px equal to x squared minus 3x plus 1, what is a differential equation of differentiation derivative of this one with respect to x will be, no, 2x. This will be minus 3. This will be 0. I don't need to write. Okay. So 2x minus 1. That's what happened. So a naught is a constant. So I don't need to write. So this will be a1x minus a1x naught. So a1x naught will be a constant again. So it will be 0. So a1x will be a1. Again, we have what is the other term? a2x minus x naught squared, isn't it? So what will be the derivative of this one? It's like a xn, no? What is the different derivative of this one? An xn minus 1, no? So like that, okay? Very simple. There's nothing big thing here. Okay, good. So here, I'm erasing this extra things. So my, okay, my term here will be is 2 times a2 x minus x naught 1, no? 2 minus 1 will be 1. Okay, this will be this. Okay, now what about we are doing successively differentiation, no? So what about the second derivative of this? So here this will be 0, no? Okay, this will be 0. So this will be 2a2. Similarly, what is the next term? Can you tell me? This will be n into an into n minus 1 into x minus x naught to the power of n minus 2. That is okay. Can you tell this term? Similarly, okay, you don't need to go to P3. Let's go up to Pn. Okay, Pnx. Can you find the gender? If you want, you can find the P3 also. P3x and find it and tell me the general formula for this one. Okay, so each term you have to notice the P1, A1, A naught term is cancelled. The P2, A1 term is cancelled. So P3, it should be A2 terms will be 0 now because it's a constant. So it goes like that. What will be the final Pnx? So you can see this one. This is like a n into n minus 1 into an of x minus x naught to the power of n minus 2. So it is coming something like a form we already know. So what is that form? That is what I need. Can you find the general idea? 60, yeah, maybe correct. So I need the Pnx. Can you derive the final output of Pnx nth derivative? Okay. Number 26 not yet answered, no? 026, can you answer me? And also, let's see some people. Hundred and 59. 35 as well as 151. Can these people answer me? What is the final Pnx? Okay, good. 004, correct. So you should have the idea of how to find the general form from 103 equation, isn't it? So if you know 1, 2, 3, all are following some pattern, you should be able to find the final general idea. Okay. I'm still waiting for your answers and of course these people's attendance. Twenty-three. No, check your answers. So why taking this much long? So we already know P of x equal to A naught plus A1 x minus x naught plus A2 x minus x naught whole thing square up to, we are going up to an x minus x naught to the power of n. Okay. So P dash with respect to x. So this will be 0. This will be. So A1 plus. So if you take this one, 2A2 x minus x naught. It continues like that. And NAN x minus x naught to the power of n minus 1. So P2 of x. So P double bar is just equal to. So I can either tell first derivative, second derivative. This will be 0. This will be 2A2 plus this third term will be A3. So 3A3 x minus x naught squared up to this one will be n into n minus 1 into an into x minus x naught, the power n minus 2. So if I go like that, so in some point of Pn of x, all these term will be 0, 0, 0. This only will be balanced. This will be n into n minus 1, n minus 2, up to 2, up to 1, and an only balance. This will be x minus x naught to the power 0. This will be 1, no?